Morning all, I hope you can hear me. Let me know if you can't. Um, so you can let me know in the online chat. I'm just briefly coming in. The lecture will start at 10 o'clock. So I notice that there's quite a few people logging in, so that's good to see. Okay, so the lecture this morning is on wireless technology. So it'll start at 10 o'clock. I hope you're all keeping very well, safe and sound. So I'll just disappear for a minute again now, if that's okay. Morning all, I hope you can hear me. Let me know if you can't. So you can let me know in the online chat. I'm just briefly coming in. The lecture will start at 10 o'clock. So I notice that there's quite a few people logging in, so that's good to see. Okay, so the lecture this morning is on wireless technology. So it'll start at 10 o'clock. I hope you're all keeping very well, safe and sound. So I'll just disappear for a minute again now, if that's okay. Morning all, I hope you can hear me. Let me know if you can't. So you can let me know in the online chat. I'm just briefly coming in. The lecture will start at 10 o'clock. So I notice that there's quite a few people logging in, so that's good to see. Okay, so the lecture this morning is on wireless technology. So it'll start at Actually, I'd be grateful if anybody's listening here, which I hope you are. If you could just sort of sign on an online chat, just let me know that you can hear okay. I'd be very grateful because I don't want to be talking to a blank screen if that's helpful. So I'll be looking out in online chat to see that you can hear. So if one or two of you could just let me know that you can hear loud and clear, I'd be very grateful. Thank you. Okay, good morning. Good morning all. I was just typing in the Blackboard attendance there, which is 8488. So please do sort of register your attendance. It is funny, as usual, talking to a screen. So anyway, here's the lecture, and I'll get on with it now. Okay. So lecture number 22, and today it's about wireless technology and wireless communications. So I hope you're all keeping very well and good, and I certainly am at the moment anyway. And I won't say totally enjoying this, this period of time when, we're all, I suppose, spending far more time at home than we would normally do. But it's fine, and it's quite interesting trying to put together a lecture in this fashion, because it's not actually that easy to do it technically. Or not for me anyway. Not maybe you lot would find it a lot easier than I do. Anyway, just to go through the various points. Obviously we've gone through 50% of the course in the first semester. As you know, most of the assignments are in now, and most of you have put your assignments in. I am urging any of you, please, who has not put in an assignment yet, and there are one or two, to send them in by email. You can still submit them, and we're going to be giving you plenty of latitude this year. In that by the end of the semester, we'll still take assignments up towards the end of the semester. But obviously, I want to get them all done and dusted, and you should too. So this Wednesday, we're going to start our live lab test, and basically it'll start at 12 noon online. Myself and the lab assistants will be available to you on Blackboard to discuss this if you wish, if you're not clear about anything. I sent out a video last night which I'd urge you to watch. The video basically describes what I'm looking for in terms of using codepen.io, and how you can display that in your answer, in your question. So basically it's a case of making sure that you cover all the things that are asked for in the lecture, or sorry, in the test, and put them into the correct boxes in HTML, CSS, and into JavaScript, and then copy them under the headings of HTML, CSS, and JavaScript into your answer. So what I want to be able to do is simply recreate what you have, which is to just simply copy your HTML, your CSS, and your JavaScript into CodePen and get exactly the same thing that you can see on your screen. So that's basically the format of the question. So it'll be similar to the mock lab test. Anyway, thank you to those. Many of you did actually manage to grasp this and to get this in the mock lab test, but not all of you, so I just wanted to go through it. Okay, as I said, this week at 12 o'clock, there'll be 3 attempts. They're about an hour. We'll give you 60 minutes to do the lab test each. So we're starting at 12 o'clock, but don't mind, because basically we'll be available from 12 noon until 3 o'clock on Wednesday. And if you have any queries about it or any questions, it might be no harm to ask us in advance. So you're welcome to come into Blackboard, and we can either talk to you one-to-one, or go through the various points to do with the test or to do with the assignment, or if there's any other questions you want to ask, feel free to do so. Okay, so today's lecture anyway is on wireless communications, and basically just to define wireless communications, they're a type of data communication that is performed and delivered wirelessly, which is a very broad definition really, and it incorporates all procedures and forms of connecting and communicating between 2 or more devices using a wireless signal through wireless communication technologies and devices. So the key thing, as you've obviously guessed, is that we're talking about things which don't involve wires anymore, which is potentially a good and a bad thing. Okay, so it goes right back. When I looked at this first, I said 1980s, but in fact it's 1890s. Goes right back to the 1890s, when there were first experiments transmitting telegraph by radio. And in the 1920s, work was done in terms of telephone by radio, and radio and satellite for long distance communication has happened since then. And wireless communications are used in local area networks these days. And wireless does not just mean mobile, it can also be fixed. We can have sort of fixed devices which communicate through wireless technology. For example, you might have a local area network server which communicates wirelessly with a base station which is maybe slightly more remote than other base stations and can't be connected by wire that easily. So transmission technologies, things like infrared and spread spectrum, and in terms of standards, our old friends IEEE 802.11, and I'm sure you're all going to memorize that, and it's going to be etched on your brains. Okay, small wireless communications. An example would be a remote control for television, for example, and that works by a light beam. So you'll notice generally with remote control for television that if you're not pointing it at the television, it doesn't work very well. So, and if you're in another room in the house, and I always thankful about this because certainly my kids always had great laughs sort of standing, you know, at the door and changing channels and me wondering what the hell was going on. But anyway, that's not something, sorry, I've got a frog in the throat. I haven't got the coronavirus, I promise you. Yeah, but like it is a point and click device, remote control, so it uses a light signal. It works over a limited distance and it does not travel through walls, so line of sight only. So I did cop on to my wonderful son who would be pressing the remote control and annoying the hell out of me. So what about radio-controlled toy cars and door locking systems on cars? I think many of you be familiar, well, many of you have cars obviously, but you know, it's quite a familiar thing nowadays to use a remote control device to open the car door. I find it wonderful because it means I can just sort of pull the keys out, walk away from the car, and then do a double click. And I have this wonderful thing where if I double click on it, the mirrors go in. And what that does is does two things. It keeps the mirrors safe, but it also, the wing mirrors I'm talking about, but it also tells me that the the car is properly locked, and it doesn't work on my car unless the wing mirrors actually go in. But these are all very handy little devices. You know, they're do we need them? Marginal. I mean, keys worked fine, but you know, nevertheless, they are quite handy little devices. So radio systems which transmit and receive, an example would be cordless phones. So I'm not talking about mobile phones now, I'm talking about cordless phones, which basically we'd be talking about a base station and we'd be talking about a handset which transmit to each other over a few hundred feet. And those are susceptible to noise, and they may be linked to PABX to enable employees to carry cordless phones with a number of base stations networked and providing an effective cellular system. So that would be common in certain companies, but it's probably becoming less so with the advent of mobile phones, which I'll come to later. So each node has an antenna which acts as a transmitter and receiver of electromagnetic waves, and the parabolic antennae are directional within a certain sector. Omnidirectional, they fill the entire space within the radius, which is shared medium, and having unguided signals causes problems. So there can be security issues in relation to this, so there may be a need to encrypt, and also there can be interference, which none of us really like. So there's just an example of omnidirectional antenna and directional antenna. And now I promised you that I was going to look at your any questions you might have, so if you haven't typed them in yet, I just have to flick screens here. Sorry. Online questions. No, I'm not getting any online questions. I can see that you can hear me, but I haven't had any other online questions. But if I do get any, I will endeavour to answer them as best I can. Okay, sorry, just 1 second. Clicking boxes here. Okay, don't all go away now that I'm pausing, please. Okay, I'll get back to the slides. Okay, so signal characteristics. High frequencies are necessary for fast data transmission as at a higher information rate. Poor penetration through barriers such as walls, and faster signal decreases with distance from the transmitter. And low frequency signals up to 2 megahertz. Please look up megahertz and work out what megahertz, what that measurement is all about. But they propagate along the Earth's surface. And control is needed for sharing electromagnetic spectrum, and this is done by licensing, and licensing by government bodies. So you can see a diagram there of the electromagnetic spectrum, and you see the various different types of rays. You've got radio waves, microwaves, which you'd commonly associate with cookers, but they can also be used for communications as well. So infrared waves, then you've got UV waves, X-rays, for example, people will be very familiar with those, and gamma rays. So all these different rays are available on the electromagnetic spectrum. So there's a nice diagram, signal characteristics, and you can see the difference there between reflection, scattering, and diffraction. So basically signals can be propagated by those three methods, but the receiver can get several copies of the same signal using multipath propagation, and sometimes that leads to distortion. So there can be inter-symbol interference and multipath fading. So basically systems need to be designed well, communication systems need to be designed well so that we don't get distortion to the various different devices that we use. Okay, so point-to-point systems are used for radio relay. Several high towers in line of sight using parabolic directional antennae, and each link is transmitted on microwave frequencies in narrow beams. And these are used by communications carriers, also to link two buildings in a city, or for communications of two computers in the same room instead of infrared. So that's one way to do it, point to point. And there's various different systems, as you see. You might think that a lot of these things are transparent, but they're all very carefully thought out. And really, it depends on the particular situation as to what communication system is actually used. So point to multi-point systems, multiple terminals connect to the base station, often in a high tower, and usually antennae span a specific sector, say 45 degrees. So several antennae to ensure full 360-degree coverage. And as you can see the diagram there, there's various different towers connecting to each other. And in terms of buildings, as you can say, the 360-degree issue is quite crucial. So you might find, for example, in some cities, the local government or whatever, the city governance uses particular communication systems like this. Now, we'll be more familiar, and I'm sure lots of you are using cellular telephones at the moment. You might be watching this on a cellular telephone, which is, of course, a wireless device. I'll hold up this wonderful mouse that I use to click between a wireless mouse, which is a great invention as far as I'm concerned. It allows me to, I suppose there's two key things. There's the infrared nowadays, instead of a little ball at the bottom, and the fact that it's wireless sort of makes it much easier to use on a, instead of getting tangled up in all sorts of other devices, the cables from the keyboard and all this sort of thing. So it does help. Wireless technology does help to make things actually easier for us too. So in terms of mobile phones, it's a cellular system, as you probably know. Sometimes you notice that the sort of signal, if you're driving in a car and you're going through different cells, you might notice a slight distortion on the phone as you go through them, the different cells. And it's particularly profound on the train from Galway to Dublin, for example. I find that there are some patches where, in fact, there aren't very good signals for mobile phones. So you'd be talking to somebody and suddenly you'd lose them. And that's because you've gone from one cell to another, and the second cell isn't either working properly or it's not picking up properly. So the point is the cells kind of overlap, and the system knows automatically when you travel between different cells. So they're very useful for actual transport and you know, if you're actually walking around or you're driving around or whatever way you're getting around. So again, they use base stations, antennas or towers. Usually they're small cells which they cover several miles in a honeycomb pattern, and neighboring cells have different frequencies so that they can differentiate from each other, which is quite important. So they employ the frequency reuse in neighboring cells to limit interference, and the handoff ensures signal for mobility. So when you go through one cell into another, when the different frequency is picked up, your device automatically works all that out for you. So it sounds, usually, if it's properly implemented, that you know, it's all very transparent and the conversation doesn't stop. But you might hear a sort of slight little distortion or a click as you move along the road. That's because of the cells. So mobile telephony, they uses the Global System for Mobile Communications, GSM. It's the most popular standard for mobile phones in the world, used by 1.5 billion people when this was written, across 210 countries. I would suspect that that number has significantly increased nowadays. It's adopted by the European Union, of course. GSM cellular uses different sized cells: macro, micro, pico and umbrella. Umbrella, very interesting word always. Both signaling and speech channels are digital, and you notice that's 2G. We hear a lot about 5G at the moment, so I mean things have moved up from 2 to 3 to 4, and you know 5G is potentially being rolled out now, although, and there is some in Galway, but potentially 5G is not available yet. And 5G actually requires much smaller cells because it's much more powerful. So there would be a lot more cells using 5G than there would previous versions like 4G and 3G and so on. So subscriber identity module allows the user to retain all details using different handsets through, although operators try to lock this. So the SIM card you're familiar with, and SIM stands for subscriber identity module. So as you know, you can move your SIM card between one phone and another phone, and basically it allows all your details to be carried between the different devices. So there's a picture of a tower. You'll be familiar with other ones. Some of them are sort of towers which are hidden by made to look like natural trees and this sort of thing. So some of them are kind of designed in a more pleasing to the eye fashion than that particular one. So what about satellites? Satellites, some people think that all sort of, I suppose, cellular towers will be replaced eventually by satellites. Who knows? But these were first mentioned in science fiction. I remember reading a book by a gentleman called Arthur C. Clarke, which talked about communication satellites, and he claims to have invented communication satellites. But anyway, it is something which has come from science fiction. The Soviet Union, as it was, the USSR, launched the first satellite in 1957, and that started the space race. So in a way, traveling to the moon is one thing, but the satellites and communication technology is far more widely used than actual human travel to different planets and to the moon and so on. So satellites play a role in, I suppose, everyday communications and technology. But in 1962, the first American telecommunications satellite, Telstar, was launched with 600 voice channels. So look up Telstar now; it's quite an interesting thing. We can now connect with terrestrial stations and with each other using satellites. So signal transmission similar to microwave signals on Earth, except node is in flight. So basically we can bounce our signals off satellites. Satellites can allow us to communicate over, I suppose, a much wider range than, obviously cell towers and so on. So orbit is elliptical following Kepler's laws, classified as GEO, MEO and LEO, and we'll get to that in the next slides. So geostationary, that's GEO, geostationary satellites, they hang above the location above the location on the equator, and they move at the speed of the Earth. So they act effectively as a fixed antenna. So as the Earth spins round, so does the satellite. So they just sit there hanging above us. They can cover a quarter of the Earth's surface, so it's easy to broadcast to an entire country. So one satellite can do for Ireland, for example. It's above the Earth's atmosphere, so the height does not deteriorate usually, and requires a large antennae, 10 meters in total in diameter. Think of 10 meters. I'd be about just under 2 meters. Well, I'd be under 2 meters tall, but there'd be 5 of me standing on top of each other. So that's quite a wide antennae. But it's directional on a satellite and can support a 1 meter diameter. Sorry, I'm terribly bad. I haven't looked at your questions yet again, so I'll just sort of deviate again. I can't see any questions. Can't see any questions. Anyone want to write anything or type anything? They're welcome to do so. Thank you for liking it, a few of you, and good to see that there's plenty of you still there. So I'll go back to the slides. Sorry about this. Okay, so back to our satellites. It's above the Earth's atmosphere, so the height does not deteriorate. Usually requires a large antenna, as I said, and we discussed the size of that. They support telephony and data transmission, which is very important indeed, because a lot of data is now transmitted by satellite, and obviously conferences, specific conferences, can be supported by satellites, specific satellites. So delays often occur due to distance from the Earth, and signal losses can be high, which is an issue, and obviously this is one that's being technically worked on a constant basis. There's poor coverage at the poles, so any of you polar explorers out there, if you're standing at the North Pole, I'm afraid bad news for you. On two fronts: one, global warming, you might disappear into the sea at some stage, and the other one is very poor coverage from satellite technology. So since satellites can be no closer than 2 degrees to another, a max of 180 is possible. So, you know, they have to be very carefully politically controlled, because obviously if every country is sort of whipping up satellites, and it's much easier to do so now. I think Ireland's first satellite was launched recently, but you know, they have to be sure that they don't sort of smash into each other when they're zipping around the Earth, or indeed when they're stationary. So it is very important that these are actually mapped and controlled by the different countries. So MEO satellites, they're used for GPS, and you'll all be familiar with GPS. So the Big Brother is watching you system. Right now, you know, your own location, if you've kept GPS, you know, if you're allowing people to look at your locator, you know, people can find out where we all are if we have our mobile phone with us. And basically GPS is enabled in computers, it's enabled in mobile phones, it's enabled in a lot of devices. But similarly, we can see a lot of things using GPS. It can be used, for example, to see where the next bus is physically located in various apps which are available nowadays. They're not great for Galway, but you know, in Dublin there's fairly good apps which allow you to see exactly when the next bus is coming, and in many cases can estimate how many minutes for the next bus or the next taxi or whatever. So they're used for determining user coordinates. So obviously people will be familiar with coordinates, latitude and longitude, and every single sort of spot on the Earth has its own individual coordinates, which are sort of divided into degrees and minutes and seconds. So where I am now has a specific numerical reference, and I can be found by GPS if I have a device, which I do. I have one here, so there's probably a satellite looking at me right now and knows exactly where I am. Not that it necessarily cares, but it's possible to do it. So we're talking about only 24 satellites using ground-based networks for tracing, and many receivers. So many different applications are coming on stream using this technology, and it can be extremely useful. So what about LEO satellites? They require reduced power as they are closer to the Earth, and they have a short propagation time, and that can be advantageous for some types of communication. but they have a small coverage area which revolves every 2 hours, so it's visible to the Earth, and station for only 20 minutes though. So these were basically started off in the 1997 Iridium project. So you can see what the logic of that is. You can see a graphic now which shows you the different types of satellites and their distance from the Earth. So obviously you'll appreciate the further out they are, the wider the area that they can actually cover. I mean, this is just simple geometry, I suppose. Okay, just let me catch my breath, and I will also have a quick look at any questions to see if any of you has asked any questions. I haven't seen any yet. No. Maybe I'm missing something. Maybe you all are asking questions, but I don't think so. Okay, so radio. Radio is something which is quite, we're all quite familiar with. Now, there's many different types of radio, and I've been doing some work with a group in Germany called Deutsche Welle, which is the the German what do you call it, World Service type of system. So they were very upset, a lot of them, when the analog system was turned off, which basically means you can't get the radio by by normal means that we're used to in Ireland, which is on a sort of transmitter using radio waves. They've gone totally digital, so it means that we're familiar with that in terms of the television. In television, signals in Ireland have gone totally digital, but we still have the analog radio. And I think in times like the present, it's actually very helpful, because what would happen to us all if the internet, got disrupted in any way, if there was a problem with it, if, there was, it's basically an alternative means of communication. So as you see, basically analog radios using the RT radio stations in Ireland, there's many different transmitters around the country, and it's a very traditional way of broadcasting. And famously, there was a big transmitter in Athlone which used to transmit right around the country, and in old-fashioned radios, it would actually, the word Athlone would actually be written on the dial of those. I remember that. And Athlone is very useful place because it's right in the centre of Ireland, and therefore it has a very good radius. But the different types, obviously, RT Radio 1 is broadcast on FM, frequency modulated. RT Radio 1 is also broadcast still, I believe, on long wave on 252 kilohertz. So that's actually available right around the world. So long wave is actually an interesting one. I think the BBC World Service is broadcast on long wave as well, and can be picked up right around the world. So RT2 FM is again obviously broadcast on FM. Lyric FM obviously the same, and Radio na Gaeltachta is listed there as well. So several VHF FM main transmitters in strategic positions around the country transmit the FM service throughout the country, and additionally many auxiliary transmitters serve local areas where signals from the main transmitters are known to be weaker. So if you're out in Belmullet any day soon, you'll notice that you'll know that in fact auxiliary transmitters are probably helping you out there. So let me go back to my PowerPoint slides. Okay, a digital audio broadcast, DAB, radio is the only receiver at present that is capable of receiving all of RT's transmitted radio content. The RTNL DAB MUX multiplex on channel 12C, you can read the numbers, megahertz, has a 54% population coverage and is available in Cork, Limerick cities and the Greater Dublin area. So digital only stations, RT Gold, RT2XM, RT Choice, RT Junior, RT Pulse, RT Radio 1 Extra would be used on that. All RT's national and digital radio services are available on Sairview or satellite TV. So some of you will be familiar with Sairview. Obviously there are many other different sort of media transmitters, different satellite transmitters, Sky for example, or Virgin Media, I think, tends to transmit over the cables. But we're talking about wireless here. So wireless LANs transmit data through the air rather than through wire or cable. So people were asking me last week about LANs. There's many LANs within the college. So some of them, I believe, do use wireless technology to transmit. So the NIC installed in computer is connected to an external radio transmitter, and sometimes only wireless is used between different hubs. So that can be helpful, for example, if hubs are in different buildings. They can communicate by wireless technology. So the advantages, obviously, of wireless over wire is that you've obviously got no wiring problems in older buildings, for example. So many of the modern buildings are designed with cables embedded in them, and as we discussed, very significant capacity actually embedded in them. But the older buildings can be quite a problem, because obviously drilling holes in the walls can be a bit of a nuisance as we upgrade our systems. So the disadvantages are increased capacity for noise, slower data rates, and that is a problem. Obviously, if you're using Wi-Fi or whatever, we'll come to that in a minute. It's a slower data rate than if you're connected to a cable, or at least it is at the moment anyway. So there's also an issue of lack of security, because obviously if computers can pick it up, at a local level, then other computers can potentially pick it up. But obviously it needs a level of encryption, so therefore that will prevent people from hacking into it. But it is possible that people will pick it up. To be honest with you, people can also pick up, there's other ways of reading even sort of computers which are wired only. So don't think that if you have a computer which is connected only by wires, it's possible to read VDU radiation potentially as well. So advanced spy systems can read not only wireless broadcasts, but also they can actually examine wired technology from a distance too sometimes. So we'll be familiar with Bluetooth, which is sort of a localized system. It's for small linkages, and there's your standard IEEE 802.15. Wi-Fi was intended to be used for indoor mobile wireless access, and it generally is, but now many providers in airports and other public places are using it. And obviously in Galway City there is an attempt to provide free Wi-Fi right throughout the city. It's being offered in many towns. Monaghan, I remember, was one of the first ones in Ireland to be fully covered. There are obviously political issues relating to this, mainly not technical issues, because basically lots of different businesses, for example, might like to provide Wi-Fi under various different circumstances and potentially advertise using Wi-Fi. But also, there's some people who don't like the idea of Wi-Fi, and the political sort of coverage is quite important, particularly in some places rather than others. So WiMAX is broadband wireless. So broadband wireless is actually quite common nowadays, and broadband wireless is obviously very powerful. WLAN. WLAN uses radio to send data between NIC and AP. It is important to ensure that access points or APs do not conflict with each other. Therefore, each access point is set up to transmit on a different part of the frequency range. So you see these numbers, 2.4 and 5 gigahertz frequency ranges. Sometimes if you have your own Wi-Fi at home, you might find there are two signals, a 2.4 signal and a 5 gigahertz signal. So users can roam from point to point and initially select a channel based on strength of signal from an access point. So during roaming, if they're detected with a stronger signal, it attaches itself to this particular access point. So it's possible also to get things like boosters to boost the local LAN as well. So if you have a weak signal in, let's say, an upstairs room in your house or a different room in your house, it's possible to actually purchase signal boosters as well to enhance the signal. So usually a set of APs is installed to provide geographic coverage and meet traffic needs. So that's for obviously the wider you know, wide area LANs, yeah. So channel A, channel B, channel C, channel A, yes, you can see all that on that particular diagram. So you've got your transmitters and your receivers. So designing the WLAN infrastructure, the physical design requires a site survey to determine the desired coverage and interference points. To position access points, importantly, usually at an overlap of about 15%. So, for example, if we're designing a WLAN infrastructure for Galway City, we need to make sure that we have access points right around the city, and as we said, a 15% overlap in the different access points to make sure that there aren't any blind spots. And that overlap is fine because, as we said, they use different frequencies for neighboring, neighboring access points, and therefore it ensures that there's proper coverage. So in a multi-story building, signals travel up and down, so they use vertical mapping to minimize interference from access points on different floors, as well as horizontal mapping. So there would be an example. You can see channel A, channel B, and channel C. So you can see that they're sort of positioned in a way that allows for maximum coverage. Okay, Wi-Fi is a set of standards developed, as you see, by IEEE 802.11, the standards group, and it's also called Wireless Ethernet. So the physical star and a logical bus, central access points to which computers direct transmission star and radio frequencies are shared using a bus. So we saw last week the difference between a star and a bus, and a star is when you've got a central access point and that radiates out to different access points, whereas a bus is more a linear thing and it basically goes up and back and radiates out to access points along the route. So it is actually like a bus route, really, a standard bus route. I'm going to go to your questions again, just in case there are any, and I'm hoping that there's one or two, so quickly start typing if you feel like it. No, nobody saying anything on chat this morning. Okay. I hope I'm not missing something now, like I did last week. Last week everybody was very chatty, and I was looking in the comments and didn't see your chat. But this week now, there doesn't seem to be much chat going on, so interesting. So the WLAN technology uses CSMA/CA, so that's carrier sense multiple access and collision avoidance. And you'll be familiar, what we were talking about is collision, that different sort of data packets would be colliding with each other potentially, and we need to avoid that. So there's various different systems to allow us to do that. So if we listen before transmitting, and if no other is transmitting, then they proceed. So hopefully two packets won't be sent out at exactly the same point in time, because then they'll collide and there will be a problem. But obviously we have the technology to make sure that even if that does happen, that the packets are just simply resent. So this all happens in microseconds and milliseconds, and it's pretty transparent to the human eye. So in terms of security, SSID, service set identifier. So an SSID is required by all clients to include this in every packet, plain text and easy to break. So the wired equivalent, wired equivalent is WEP, and that requires that a user enter a key manually. Um, so communications are encrypted using that key. The short key is 40 to 128 bits, and it's easy to break by brute force. So extensible authentication protocol is one-time WEP keys which are created dynamically after login, and that requires login with a password to a server. And WPA is the one that many of you will be familiar with now. It's the newer standard, and it has a longer key which is changed for every single packet. So those are the different types of identifier on packets of information, and you may have come across them at some time when you're trying to set up your Wi-Fi, for example. WPA key and WEP key. So they're different levels of security, and obviously the recommendation there would be the WPA is the the best security. So what about the future for WLANs? Mobile workers have any data, anytime, any place. Public access hotspots become more popular, and that drives demand, leading to ubiquitous Wi-Fi, which means Wi-Fi everywhere effectively. That is kind of happening. And development of new internet technologies. There's new internet technologies being developed every day, and even in this time of lockdown, and well, it's not exactly lockdown, but even in this time of that most of us are working from home or staying at home as much as possible, there are new technologies developing, and in fact, it's quite a challenge at the moment, because obviously communication systems, we're having to be quite inventive. An example would be this lecture, for example. I don't know, I've heard of lots of other different ways that lectures are actually happening, and I think it depends to some extent on the type of lecture or the type of subject you're discussing, because obviously things like microbiology lectures, where normally you'd require quite, I suppose, physical lab work in using various different, different microbes and so on, would be quite different from this sort of course, which is simply looking at computer technology. So I mean, most of this is quite handy for the type of medium we're giving it to you in, but not every type of lecture obviously can be done in the same way. So people are having to be inventive. So I think a lot of development will probably happen as a result of this worldwide crisis, and certainly communications will probably change as a result. So I mean, that's a good thing. WLAN technologies are vying with mobile phone technologies, and they certainly allow for prices to drop. So I mean, many of you will be using apps, for example, that allow you to communicate for free rather than paying a fortune to the mobile companies. So there is an issue there in terms of communicating using WLAN, or using I suppose more standard mobile technology. So there's an ever increasing demand for WLAN technology, and rightly so, because I mean, obviously we're all price sensitive really, and we don't like paying for things which we can get for free. So that's pretty much bringing us to the end of this week's lecture, but I do want to say that this week's lab test now is very important, because it's 25% of this semester's marks, and basically it's a one-off. So this actually, the lab test will be similar to the mock lab test. It'll have a section on multi-choice questions, and it will have a single question relating to HTML, CSS and JavaScript. So the way I've described it in the previous video, please look at that video, please get an example, and please look at the example that I've given you on the resources on Blackboard. If you're not sure how to find it, just email me. But you will get 3 attempts at the lab test, and it's not all going to be over on Wednesday. We'll be starting it on Wednesday, so please avail of the opportunity to come in to the lab if you wish. I'm going to take, if anybody has any questions there now, please send them to me, on the chat. I'd be grateful if you did. I'm just going to have another look at it. So just to prove it works, most of the chat this week is by me. Can you still hear me, everyone? Can anyone still hear me? Could somebody just let me know that they can still hear me and that I'm not talking to the wall. You're still listening, so you know, it's thank you for that. Go on, somebody just put something into chat, please, and let me know that I'm not talking to myself. No, okay, well, anyway, that's fine. So look, that's it really for this lecture. I'll let you go, and to those who are watching after the event, hello to you. And you know, this lecture will stay up online, so you're welcome to look back at it and just go to the bits that you find useful. There will be a test on this the final week of the lab, and we've only got 2 more weeks of labs, but the final week will have an MCQ test. Thank you very much, Martin and Shane. Yes, you can still hear me. Great, great. Thank you. Appreciate it. Do you know, it's not easy talking to a camera. Oh yeah, okay, May as well. Great, great. Well, listen, I'm hoping that you find the lab test straightforward enough, and please do email if you have any questions, and anyone who hasn't submitted their assignments yet, and please do so by email. And if anybody feels like resubmitting their assignments, if you have sent them in on time, you will get the grade for that. And if you wish to resubmit them, I'm not going to penalise you so long as you've got them in on time in the first place. So it's up to yourselves. I know you've got many other things to be doing, and I know we're all kind of worried at the current situation. You know, but that will be over at some stage. So please stay safe and well, and please do listen to all the people who are suggesting that you do stay at home. It's going to be a pain in the neck, especially for many of you. I enjoyed my student life and I enjoyed getting out and socializing many years ago. But it is a time now to be careful and cautious, because none of us wants to get badly sick, or indeed to spread disease. So please be responsible and please stay safe. So thanks very much for those who came along, and normal service hopefully will be resumed certainly in the next semester anyway. I suspect this semester is going to be pretty much online. So thank you all, and we'll try and keep things as sane and as sensible as we possibly can. Okay, so see you next week for the last lecture, and also hopefully some of you for the lab next week, and looking forward to receiving your lab tests, and they'll all be graded soon enough. Okay, thank you.